Hi there everyone. In this video I'm going to go through some of the real basics about exponential functions and the applications of exponential functions. I'm going to get the trusty calculator out, do a few little calculations. We've seen the introduction to the number e and what it's all about. Particularly you would have seen an introduction talking about compound interest. But there's so many applications in modelling population growth, spread of disease. There's all kinds of things where the number e turns up, in particular this formula here that we're very interested in, ae to the kt. So I want to explain a bit about that and also just give you an introduction of how that works with the compound interest thing that we've seen. So you would have seen where we had, we've got our basic compound interest formula where the amount, principal 1 plus r over n to the power of n. I'll write it something like that, where n is the number of time periods that we're doing our compounding for. So if you've got $1 in the bank, so I'll just make p equal to 1, that's nice. And let's say the rate was 100%. So we're just going to add on 100% of the cost, which is 1 as a decimal. And then let's say we're going to do it over the course of just one whole year. So that would tell us that we'd end up with $2 at the end of the year. And then what we saw is if we increase the time period here to see what happens to the value of our investment. So let's say we compound the interest twice a year. It would look like this. So we're adding on 1 plus a half, so 1.5. We're adding on 50% and we're doing that 2 times a year. And that ends up with $2.25. So we're doing better here. And you saw what happened when we increased the number of time periods. So let's say we then went for monthly interest. So the compounded monthly would look something like this. So we start with our dollar, the interest rate of 100%, which is 1 as a decimal, divided by 12. So that's what we're timesing our $1 by, and we're doing that 12 times in a year. And of course, what you saw is that this thing here, if we get lots of those, the limit of that sequence there as n tends to infinity is the number e. So if we do compound interest compounding continuously, every second of the day, every millisecond, every instant of time, we're adding on a little bit and then getting that money and then adding it on. So I know when you get down to it, the real nitty details here, you're going to nitty-gritty details, you're going to say, well, in an instant of time, how can you even make 1 cent in like a millionth of a second? So this is just some theory here with money that we deal in only cents. But if you think about this like sort of like a continuous thing like area or growth of, let's say, a weed infestation or something like that, or an algae bloom on a lake, then this would be appropriate. You could think of it in terms of the area covered is a continuous thing. Okay, so what about if the interest rate's not 100%? All right, so we also saw that when we do this, 1 plus k over n to the power of n, that tends towards e to the power of k, the limit of that thing there. Okay, so let's say we went for 7%. Let's say we're doing 7%. So we'd have 1 plus 0.07 over n to the power of n. So let's say if we were doing it monthly, we'd have n equals 12. That would be tending towards e to the 0.07 in this case. Okay, so if we wanted now to come up with a formula of how much money we're going to have at the end of the year, given that the interest rate we were earning is 7% and it's compounded continuously, so every instant of time. So the amount of money would be the amount that we start with, which I'll stay with p, and it would be e to the power of 0.07. Okay, that's what our amount of money we would have in the bank at the end of the first year. Now, what if we wanted to go for 2 years? Well, it's the same thing, except we're doing it for another year. So it would just be this to the power of 2, or 3 years would be this to the power of 3, etc., etc. So the amount we would have in the bank would be, notice we've got a power to a power here, so we'd multiply these two together. So you go e to the 0.07 t, where t is time in years that we were doing. Okay, cool. So in general now, I'm getting real general here, we could have this formula here, e to the kt. And that's the formula that the syllabus mentions. And the reason I went through all this so you understand it. So that's our initial amount there. E is Euler's number, as we know, continuous compounding. K depends on the rate. So if you're increasing something by 20%, that would be 0.2 there. If you're decreasing by 10%, that would be a 0.9 there. Those kinds of things. So your value of K there, and then T is time in years, or the number of time periods that you're looking at. Okay, and that's the total amount over there. So that formula works not only for compound interest, but all kinds of things. So let's just do one example of how you're going to use your calculator to do these kind of things. So imagine we have $1,000 in the bank and we're earning 12% interest compounded continuously. Now, by the way, that is like foolish to think that would happen in today's economic climate. You might likely to get 3 or 2%, but let's say we've got 12% compounded continuously. So we don't just earn 12% at the end of the year, we're earning a little bit of money every instant of time. So the amount of money that we're going to end up with is our initial $1,000. It's compounded continuously, so E, and it's 0.12t, e to the 0.12t. That shows us compounding continuously. So we might now ask questions like, how much money have we got in the bank after 5 years? Very simple. So if I ask that question, how much we got in the bank after 5 years? You'd have your $1,000 to start with, e to the 0.12 times 5. Okay, that's how much money. So on my old calculator, it's shift the ln button, which gives you e to the power of, and I normally put brackets as well, which is really helpful. 0.12 times 5, close the brackets. So I do the e part first, and then times that by 1,000. This tells me 1,616. You could leave it to the nearest dollar. That'd be fine, but it would be in 7 cents as well. Next kind of question that you need to know is, how long would it take for me to have $8,000 in the bank? So in other words, I'm giving you this and I'm wanting you to find the value of t there. Okay, so here's the equation. 8,000 is the value of A, and we want to know what is the value of t in that expression. Now, the way that you solve this mathematically is using logarithms, which we have not done yet. So this is where you're going to grab out your calculator and use the solve function. So it's just a matter of setting it up, getting it right. So if you grab your calculator, put that in and click solve, your calculator will spit out 17.32867 blah 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 years. Okay, and if it asks 17.3 years would be a good way to round it. I mean, you could technically go months and days and hours and minutes if you really wanted to, but 17.3 years is when you'd have $8,000 in the bank. So there's some really simple problems there of starting with this exponential function, the idea of exponential growth, and being able to do something with our calculator in a question kind of like that.